All right, so quick reminder, guys, that your West Edmonton Mall assignments are due tomorrow. Okay, the Galaxy Land assignments due tomorrow. Make sure you have spoken with your group. Okay, find some time to double check everybody's work. Right, the worst thing you want to do is just say you do this part, and just assume everyone does everything right. Okay, you always want to check over each other's work to make sure, because you're sharing the mark. So make sure that you're sharing the mark you want and not the mark you'll get. Okay. Second thing, yesterday we went over properties of waves, okay? And we said, we talked about things like amplitude, we talked about wavelength, period, frequency, all of that kind of stuff, right? The most important properties of a wave in terms of its behavior are the speed of the wave, the frequency of the wave, and the wavelength of the wave, okay? Those are the three most important properties. Now, we said yesterday that one of those three properties will not change once the wave is produced. Which one was it? Frequency. All right, so the frequency of a wave can't change once the wave is produced. That means that if other properties change, like wavelength or speed, they have to change in response to each other. If they don't, then there's going to be something weird about the wave. All right, so these behaviors are governed by what we call the universal wave equation, and that is V equals frequency times wavelength. Okay, now, what do the units for speed come out to? Meters per second. All right, what are the units for frequency? Hertz, or per second, right? And then the units for wavelength would be in meters. Will we get meters per second when we multiply those? Yeah, because hertz is per second times meters, meters per second. Okay, so we'll get the right units using that formula. It can also be written like this. It doesn't show that on your formula sheet because we simply assume you can do that simple manipulation that F equals 1 over T. Okay, so it could also be wavelength over period, which again will get you meters per second. Okay. All right, now I think we talked about this example yesterday. Sorry, board's out of alignment again. All right, so the example we talked about yesterday was that just out by the stoplights there on Northridge Drive, the speed limit of the road inexplicably changes from 100 kilometers per hour to 60 kilometers per hour. Okay, when cars go from one speed limit to the next, okay, they have to obviously slow down unless they want a ticket. Okay, so out here in the 100 kilometer an hour speed limit, okay, cars are spaced like this because obviously your following distance needs to be bigger if you're going faster. Now, this first car enters the 60 kilometer an hour area before the others and slows down. So what happens to the distance between it and the next car? It shortens, right? Because this one's still traveling at 100 kilometers per hour, so it's naturally going to catch up as it slows down. So if I have an observer here, he or she sees cars moving very quickly, okay, that are spaced far apart. An observer here observes cars moving slower, spaced more closely. What do they both see the same? The number of cars that go by every second. Okay? The frequency of cars doesn't change regardless of the speed or the distance between them. And the reason for that is when the speed goes down, so does the distance between them. And this is also true, okay, if we're looking at the universal wave equation. If I manipulate it so it's solving for F, that's going to be V divided by lambda. If F can't change, that means if V gets bigger, lambda has to get bigger by the same amount. So if I doubled V, wavelength has to double. All right, in order to keep frequency from changing, they have to change in exactly the same way by the same factor. Everybody all right with that? Okay, so this is an easy formula to use, right? But it's the most important one for the rest of this unit. Universal wave equation governs essentially everything in the rest of this unit. So nice, because it's nice and easy to use. Only a 3-variable formula. It's like manipulating V equals D over T, because really that's what it is. It's just for waves. But some of the contexts can be confusing if we don't read or interpret them correctly. So there's a lot of visual interpretation that goes into solving universal wave equation problems. All right, so that's what we're going to kind of look at today. Okay, so what affects the speed of a wave? That's one of the things we're going to talk about, and then using the universal wave equation, we'll go over some example problems and things of that nature. All right, so waves, it's hard to measure the speed of a wave, right? Because the speed, a wave doesn't have really defined boundaries. So it's hard to say, okay, here's where the wave starts, here's where it ends, and I'm going to time it between these 2 points. It's hard to do that because waves don't always travel in perfectly straight lines, and there's all kinds of factors and things like that. So it's easier to calculate the speed of a wave using things that are easier to measure, and that is frequency and wavelength. Those things are easier to measure. So that's where the universal wave equation comes from, right? This is a diagram of something I tried to draw for you yesterday, and that was out in the deep ocean, waves travel very quickly, but as they come close to shore, they slow down. And when they slow down, their wavelength decreases. Okay, and that's why they get taller, why they rear up and curl, okay, and look a lot different as they get closer to shore. Okay, the reason for that, the medium in which a wave is traveling determines the speed of the wave. All right, all sound waves, for example, right now in this room travel at 340 meters per second. It doesn't matter whether I'm whispering or whether I'm shouting, they all travel at 340 meters per second because they're traveling in air at about 20 degrees Celsius. Okay, the properties of the medium, the air, determine how fast sound can travel. Everybody with me on that? Okay, so it's the same for water waves. Out in the ocean, where the water is very deep, waves can travel very fast. But as they approach shallower water, they slow down because the properties of the medium, mainly depth, have changed. And as a result, the properties of the medium change, the speed of the wave changes, the wavelength of the wave changes. All right. Now, again, the frequency of the waves is not going to change. Okay. Like, for example, if I shine a red light from air through a window and then out into air again, does it change color? No. But as it traveled through the window, the light actually travels slower through glass than it does through air. But it doesn't change the color of the light. The color of the light is determined by the frequency of the light. The wavelength and the speed change, but the frequency stays the same. All right, everybody okay with that? Well, you could filter it, but then you're not really changing the frequency of the light. You're just eliminating the frequencies that aren't what you want, right? Like if I take white light and run it through a blue filter, all I get is blue light because all the other stuff got reflected. So no, I can't really change the frequency of it, no. All right, everybody okay with that idea? Yes? Okay. All right, so when we're dealing with waves, okay, we use the characteristics that are easy to measure to determine velocity, okay? So we get V equals lambda over T, or the way it's written on your formula sheet, F times lambda, okay? That's the universal wave equation that allows us to calculate how fast a wave is traveling. Okay. So simple universal wave equation problem looks something like this. A sound wave with a frequency of 262 hertz has a wavelength of 1.29 meters. What's the velocity or speed of the sound wave? All right, so all we have to do is go V equals lambda times F. We take the lambda they gave us, multiply it by the frequency they gave us, and we get that sound wave is traveling at 338 meters per second. Okay, that's as easy as they get. All right, something a little more complex would look more like this. I want you guys to write this example down. Okay. 6 crests is not 6 waves. 6 crests is 5 waves. Okay, 6 crests is 5 waves. That's the trick to this question. Okay, you guys all had the right method, right? If you got 0.7, you all had the right method, but you assumed that 6 crests meant 6 waves. Here's the issue with that. Okay, if I draw 6 crests, so there's 1, 2, 3, 4, 5, 6. This is where I start counting. That's 1 wave, 2 waves, 3 waves, 4 waves, 5 waves. It's only 5. Okay, so if a question tells you the number of crests or the number of troughs, it's 1 less than that for the number of waves. If it says 5 complete cycles, that's 5 waves. But if it says 5 crests or 5 troughs, it's 1 less than that all the time. Okay, so what that means then is we have to find the frequency. The frequency is that there are 5 waves in 30 seconds. That comes out to, what point? I don't even remember what it came out to. So we got 5 divided by 30 seconds. So we have 0.16 repeating hertz as our frequency. Then we take frequency and we multiply it by wavelength, okay, and that's going to give us our 0.16 repeating times 3.5 meters, which is the length of the waves, and that will give us 0.58 meters per second. All right, so that's one of the tricks that can come up in a wave question. Question? You could also find the period by going 30 over 5 and then using that to get, and then going lambda over t. Either one will work, yeah. All right, so that's one of the tricks that could happen. Okay, because there aren't a whole lot of tricks to the universal wave equation, but that is certainly one of them. Okay, another one could be that they give you a question about an echo. Okay, very often you'll get a question that relates to having someone shouts at a cliff for whatever reason. Okay, and the echo comes back. So we'll just write up a quick echo question here. Okay, and look at one of those. Okay. So the trick to an echo question is that you have to remember an echo is a reflection, okay? And a reflection has to go there and back, which means that this sound travels 600 meters in 2 seconds. Okay, so to get the speed, we simply go distance over time. 600 divided by 2 gives us 300 meters per second. All right, so the time is 300 meters per second. Okay, and then we have V equals F times lambda. We're looking for lambda, so lambda will be V over F. 300 divided by 800 hertz gives us 0.375 meters as the wavelength of the shout. Okay. Now, there's lots of different types of echo questions. Okay, it could just be, somebody shouts at a cliff because they have anger management issues and that's who they shout at. Okay, or it could be, like you're mapping the ocean floor using sonar. Okay, sonar is sound waves that are being sent to, we're waiting for the reflection to come back so we know how deep the ocean floor is, things like that. So always be on the lookout for echo questions. Anytime something is bouncing off of something else, it travels twice the distance. Or travels that distance in half the time. one way or the other. Okay, it'll work out right. Okay, is that making some sense? All right. Other things that could come up. Sometimes a question will tell you, it'll be a question about sound, but it'll tell you that the air temperature is a certain number of degrees instead of giving you the speed of the waves. All right. If that happens, we have to remember, and this formula is on your formula sheet, okay, that the speed of sound at 0 meters per second, or sorry, at 0 degrees Celsius is 302 meters per second. If you look on your formula sheet, okay, there's a formula there that says V equals 302 plus 0.6 T. Oh, sorry, 332. I said 302. 332. Okay, 332. Okay, plus 0.6 times T. This T is not period. This T is temperature in degrees Celsius. All right, that way if you have a negative value, you're actually going to be subtracting. Okay, so this will always calculate the speed of sound in air at any given temperature. So if you are ever given a question that's about sound, but they give you air temperature, you use that air temperature to calculate the speed of sound using this formula here. All right, it's not hard. You just have to be aware that that's what you have to do. All right, another thing that could come up is a question will say you're dealing with an electromagnetic wave or a radio wave or light that is red or something like that. Okay, electromagnetic waves, radio waves, light waves are all what kind of waves? Okay, yes, they are transverse, but they're also light. And what speed does light travel at? The speed of light, which is on your formula sheet. 3.00 times 10 to the 8 meters per second is the speed of light. So anytime a question is asking you about a light wave, a radio wave, electromagnetic wave, okay, something like that, and it doesn't give you the speed, it's because it doesn't have to. You're expected to look up the speed of light or know the speed of light, okay, and be able to use that in the equation. All right. The one thing you don't want to do is accidentally use the speed of sound. It's considerably slower. Like 10 to the 5 times slower, okay? So we don't want to use that. I see people make that mistake all the time, and then they don't notice it somehow when they get an answer for wavelength that's just ridiculous, okay? So we don't want to have that happen. So those are two other tricks that could come up in a universal wave equation question. But like I say, a universal wave equation is not that difficult to do mathematically, but we have to be on the lookout for kind of simple tricks that can throw us off. All right, so let's have a look at this one here. Okay, if I want to generate waves on a stretched spring, so like a slinky, okay, and you oscillate your hand back and forth at a frequency of 2 hertz. So they gave me the frequency, 2.0 hertz. Okay, the speed of the waves on the spring is 5.4 meters per second. What's the wavelength? All right, so there's my givens. I have a formula that contains all of those. V equals F times lambda, and I just solve for lambda. All right, so that's going to be 5.40 divided by 2, so that should be what, 2.7? Yeah. 2.7 meters, okay, for our wavelength. All right, not too tough, right? Anybody need that one anymore? All right, I'm going to make these ones a little bigger, and I want you to give them a try. All right, so looking at question number 2. So we have a submarine sonar system, which uses echoes, okay, to determine the depth of the water. So the frequency is 325 hertz. Okay. And the sound wave bounces off an underwater rock face and returns to the submarine 8.5 seconds, which means it only took how long to get to the rock face? 4.25. Okay, so I'm just going to write that the rock face in terms of time is 4.25 seconds away. Okay, the wavelength of the sound is 4.71 meters. Okay, how far away is the rock face? All right, can I find speed with F and lambda? Right, I can use this. V equals F times lambda. I'm going to need that because if I'm going to find the distance, I need speed and time. All right, so I'm going to find the speed first. That's going to be 325 times 4.71. Okay, so the speed of sound in water is a lot faster than it is in air. And we said longitudinal waves travel better in more dense materials. Okay, so it travels really, really fast in water, 1,530.75 meters per second. Now I'm going to take that number and I'm going to put it into a V equals D over T calculation where I solve for D. And I'm going to use the 4¼ seconds, Liam, because that's how long it takes to get to the rock face. The 8½ is to the rock face and back. All right, so I'm going to take that number, multiply by 4.25, okay, and I'm going to get that rock face is 6½ kilometers away, okay, or 6.5 times 10 to the 3 meters, because we only have 3 significant figures in that question. Okay. Everybody all right with that one? Okay. How are we doing on number 3? Okay, how many people have done 3? Okay, so we need a little extra time on 3. Okay, I'll give you a few more minutes on 3 then. So for number 3, okay, they tell us that the boat is 250 meters from the shore and that it takes 3 minutes for the waves to go from the boat to the shore. All right, so I'm going to find the speed of the waves using distance and time to start off with. All right, and I'm going to use seconds, 180 seconds here, okay, just so I have that. All right, so I'm going to go, speed is 250 meters divided by 180 seconds. All right, so the waves are traveling at 1.38 repeating meters per second. All right, now that I have that, now I can look at the other information. It tells me that the dinghy rises and falls 8 times in a minute. All right, how many waves is that? No, it's 8. That's complete cycles. Rises and falls 8 times. That's 8 waves. Okay, it didn't say 8 crests went by or 8 troughs went by. It said it went up and down. That's a full cycle 8 times. All right, so we can find the frequency then because we know there were 8 waves in 1 minute. So I'll just take the 8 and divide it by 60 seconds. And that will give me the frequency. Okay, so 0.13 repeating is my frequency. Now that I have frequency and speed, I can find the distance between the wave crests, which is also the wavelength. Okay, the length from one crest to the next is the length of one wave. All right, so I'm going to take my speed, the 1.3, 89, okay, divided by 0.13. All right, so we get 10 meters per second, okay, as the, or sorry, 10 meters as the length of the waves. Yep. Okay, any questions on how those work? Right. There's little tricks here and there. We just have to read questions carefully, okay? Because obviously the math of this is not difficult, right? We have to make sure we're being careful with the interpretation. Okay, that stuff we've already covered. Okay, want you guys to try 5, actually try 5, 6, and 7. Don't worry about 8, okay? Just try 5, 6, and 7 for right now. Shouldn't have too much trouble with any of those. Okay, so for number 6, okay, we have the temperature of seawater, listening guys, affects the speed at which sounds move through it, same as air, okay? So a wave with a length of 2 meters traveling at a speed of 1,500 meters per second reaches a section of warm water where the speed is 1,550 meters per second. What would you expect the wavelength in warmer water to be? All right, so this question is indirectly asking you what property of waves never changes? Frequency. So can I calculate that using the information for the 1,500 meter per second water? Yes. All right. So what I'm going to do then is find F by going V over lambda. That's going to be 1,500 divided by 2 meters. So the frequency is 750 hertz. hertz. All right, well, the frequency is also 750 hertz here where it's traveling faster, and now I can find the wavelength in that faster water by going V over, whoops, F. Okay, so that'll be 1550 divided by 750 hertz, okay, and that will give me the new wavelength in that water. So 1550 divided by 750, okay, tells me that they're now 2.07 meters long instead of 2 meters long. Tanner, question? You were looking at that question, yeah. Okay. Any other questions on those ones? But that is the answer. I don't have the answers here. I don't have them. Yeah. Okay. We can. You know what? I'll go through the rest so that you have the answers and you know whether you did it right or not. Okay. So for question number 5, okay, we're told the wavelength. We're told the speed, so we can find the frequency. Okay. So it'll be 1500 divided by 1.25. And so the answer for number 1, okay, is that they have a frequency of 1200 hertz. Okay, for question number 1. And then for question 2, we have a speaker system that generates sound waves that have a frequency of 2400 hertz. Okay, the speed of sound in air is 325. What's the wavelength? So it's just going to be 325 divided by 2400. All right, tells us that the wavelength of those sounds is 0.135 meters. Okay. All right. Okay, try that one. I'm going to make it bigger so you can read it. Okay, I want you to try that one. All right, let's have a look at this one. So 2 tuning forks are generating sound with a frequency of 384 hertz. Okay, so we can answer C right now. Do I hear the same sound above water and underwater? Yes, frequency is what determines the pitch of the sound that I hear, and it's going to be the same underwater, above water. Okay, if you've ever watched like the synchronized swimming, okay, in the Olympics and stuff, they have like speakers under the water so that they can remain synchronized. If the people that were underwater, you know, like when they turn upside down and they only got their legs above the water, okay, they got to still be able to hear the sound the same as the people above, or they'll be out of sync, and well, then they'll lose points as it's supposed to be synchronized after all. Okay, so they hear the same frequency of sound underwater as they do above. All right, now the other tuning fork, okay, is generating sound underwater where the speed's 1500 meters per second. Now obviously if the speeds are different but the frequencies are the same, then the wavelengths have to be different. All right, so all we have to do is calculate wavelength for both. Okay, so that'll be for one, okay, wavelength will be V over F. So that'll be for the first one, 350 over 384. And then for the second one, it'll be 1500 over 384. Okay, and that'll give us our 2 wavelengths. Obviously, one's going to be much longer than the other. Okay, everybody all right with that one? Okay, I'm going to give you about a 5-minute break. Okay, then we're going to look at something else.